Okay. Hi, welcome back to our math series for Phys 241. This week we're going to be talking about cross products, and we're also going to be talking about magnetic fields and how magnetic forces interact with conducting mediums. In this case, we're going to be talking about a wire, but let's start with some cross product review. So I'm going to talk about a few different ways that we can think about cross products. The first one, which is the one we're probably going to use the most often in this class, is going to be the geometric definition of a cross product. So when we think about the geometric definition of a cross product, we're going to assume that we have two vectors. So another way to think about cross products, it is the vector product of two vectors. So what that means is you have two vectors and you output a vector, whereas the dot product is the scalar product where you input two vectors and you output a scalar that has no direction. It only has a magnitude. Cross products is you input two vectors and you output another vector. So the geometric definition of a cross product is if we have two vectors, A and B, and we want to cross them, it is going to be the magnitude of A times the magnitude of B times the sine of the angle between them. So if we have vector A going like this and vector B going like, let's go like this, and this is the angle between them, A cross B is, that is how you would define it. It is the magnitude of A, so whatever this magnitude is here, and then the magnitude of B times the sine of the angle between them. So important things to note, this has a max value, and that occurs when sine of theta is equal to 1. So you can imagine like on your unit circle, when sine of theta equals to 1, that is when it would be at a maximum, or a -1. That's when it would be at a minimum, or it could be 0. When it's 0, that means that the vectors are right on top of each other. So, or parallel to each other. When it's at 1 or -1, they're perpendicular to each other. So what I like to think about with cross products, which you learned about in 141, or maybe you took it somewhere else, but we like to think about torque. And torque is how much torque is defined as the force across like the radius, right? So when you want like a cylinder or like a disc to move, you don't want to press your force down like this because your radius is in the same direction. You want your force to go like that because it's at a 90-degree angle. So that's my best way to think about the geometric definition of a cross product, is you want things to be perpendicular to each other to have the greatest output of your whatever value you're trying to find. In this case, it would be torque. You want them to be 90 degrees. And any variation of angles would give you some sort of torque, but what you're really looking for is the perpendicular aspect of that. So what is the perpendicular aspect of these two vectors? Then we have the algebraic definition, which you could also think of it if you've taken linear algebra. This is a matrix formula, or the matrix definition. Basically, we can define these A and B vectors. Let's say that it's AX, AY, and AZ, and B is BX, BY, BZ. So these are column vectors or column matrices. You'll learn more about this if you take linear algebra. If you're doing a math minor, you're going to take linear algebra and you'll learn all about this. But basically, the matrix definition goes like this. Let's say you want to find the cross product between these two vectors. So what you're going to do is you're going to make 3 columns. One has the X direction, the Y direction, and the Z direction. And you're going to input your values for what each direction is. So for example, for A, we have an AX term in the X direction. And then we have an AY term in the Y direction and an AZ in the Z direction. And we can do the same thing for B. So we have a BX, a BY, and a BZ. So then we want to find the cross product between these. So when you find the cross product, this is what you're going to be doing. Basically, what you're going to do is first you're going to say, okay, I want to find the, what's it called? So we want to find the determinant of this matrix. So determinant is kind of a big word. You don't have to really know exactly what it means right now, but just know that this is how you would find it. So since this is a 3x3 matrix, the first thing we're going to do is we're going to find the determinant for X. So we're going to expand out this matrix to find the determinant of the total thing. So let's see. Let's start with X. So the first thing that we're going to do is we're going to say, okay, X, this is in the X direction. And when we're looking in the X direction, we're going to not look at this, the entire column of X, and we're going to make a smaller 2x2 matrix using what's left in our 3x3 matrix. So we have left a Y and a Z and BY and BZ. And that becomes our vector part for the X direction. Then we want to find the Y component. So we're going to take that out. This is just standard notation, but you always do negative Y hat or negative J hat, whatever one you're using. It's just standard practice to do that. So I always remember to do that. And now we look at what's left, what's not highlighted. We have AX and AZ and BX and BZ. And now let's do the Z component. So I'm going to highlight the Z, and then for Z, we go back to plus, so Z hat. And now I'm going to look at what I have left that's not highlighted, and I have AX and AY and BX and BY. So now we want to find the determinant of each of these little 2x2 matrices that I made. So the way you do that is you multiply these two together and subtract it from these two. So you would get X hat, and then you do the first diagonal, we call it the main diagonal. So you have AY and BZ subtracted from BY and AZ. And then we do it again for Y. So we have the same colors. We multiply BX and AZ, or sorry, we multiply AX and BZ, and then subtract it by a BX and AZ. So it's negative Y hat AX BZ minus BX AZ. And then the same thing for Z, we have plus Z hat AX BY minus BX AY. And that is how you would find the determinant, the cross product, when you want to use the matrix definition. So this is a lot to memorize, but if you memorize these two steps, so making a matrix and then finding the determinant, you can do this every single time. It's important to note when you see this that for the X direction, it only depends on the Y and the Z components, and then Y it only depends on the X and Z components, and then for Z hat, it only depends on the X and the Y. So if you're lucky, a lot of the time, these things cancel out. If you don't have, for example, if you have a magnetic field that's only in the Y direction and your current's in the X direction, then you can find the force or any other quantity by looking at by using this matrix form. So with the cross product comes the, you should have gone over this, is the right hand rule. So this is kind of shorthand for trying to find the direction of your crossed vector. So there's a few different ways that you can find and use the right-hand rule, but the one that I'm going to teach you for this time is curling your hands and using your thumb. So let's say you have two vectors. Let's say you have A goes like this and B goes like this. And that's your origin. So I'm going to point my hand in the direction of A, and I'm going to curl my fingers in the direction of B, and my thumb will give me what A cross B is. So I'm pointing my fingers in the direction of A, curling my hands towards B. So A cross B is kind of out of the page. So we would just say that A cross B is out of the page. So that's very helpful to know, especially when we're doing magnetic field questions, and we want to know what the direction a certain part of the what we're solving for is. We use cross products a lot in electricity and magnetism, so that's very helpful. However, there's another trick, and this I have to make a note. This only works if you're dealing with unit vectors. Only. So this next trick only works with unit vectors. So if you have X hat, Y hat, Z hat, or I hat, J hat, K hat, they only work with the main three vectors like that. So if you have some linear combination of these two, though, this will not work, and I want to emphasize that. So I like to make a little circle like this, and then some little arrows that go like this. So this is helpful for just some short term, like short, if you need to know like the direction of it something quickly, and you know that they're only in unit vector form, you can say, okay, I'm going to start at X and I want to know what X cross Y is. It's going to be Z. So X hat cross Y hat equals Z hat. And then similarly, if I want to know what Y cross Z is, it's going to be X. So Y cross Z equals X. And then we can keep going and say, if we want to know Z cross X is Y. So that's good if we're working Z cross X. It's Y. So that's helpful to know if we are going in that direction. And then if we say that we're going the opposite direction, so if we say that I want to know what Z cross Y is, well, it's still going to be X, but it's going to be negative X because we're going the opposite direction. So Z cross Y is negative X because we're going the opposite direction of what the arrows are. And we could keep doing that. Y cross X, negative Z. So it is dependent on what direction you're going and which vector is first. So there's one little trick that you can know if you're confused on the right-hand rule. But just remember, this only works with unit vectors, and you can't use it for a linear combination of vectors. If they're like, if we have like 3x hat plus 4y hat, and we want to find, and this is, let's say this is A and B is just like 3y hat plus 4z hat. We couldn't use this little trick because we have a linear combination of vectors and not just one unit vector. So I hope this was helpful to learn about unit vectors, and hopefully this will help you in your magnetism journey. The next video will be about current carrying wires and the magnetic field and force that it creates. So I will see you then.